welcome back, AP Calc. We are going to do some examples on section 5.1, which deals with logarithms, the properties of logarithms that are used for differentiation. And we're going to do a quick little review on those properties of logarithms, but before we do that, just want to make sure that you can recall what the graph of the natural log of x looks like. It's the inverse function of e to the x. I'm pretty sure you know what that is. This is y equals x, and e to the x is coming up like this. So we reflect over the line of y equals x. This is the function of y equals the natural log of x. And I suppose I should have parentheses around that right there, because it's like f of x. The domain of this function is going to go from 0 all the way to infinity, but not including 0. So I'm going to say x is greater than 0. This, of course, is a vertical asymptote, so the function itself is getting closer and closer and closer to x equals 0, but never actually touching it, and that's why I don't have an equal sign here. Notice there are no negatives over here as well in my domain, so basically only positive numbers can be my x values. My range. Range is how low the graph goes to how high it goes, including any gaps or whatever goes on in the middle. This is a nice, smooth, continuous function. It goes down, down, down forever and ever and ever, quite fast as well. And it goes up, up, up forever and ever. Even though you have to go to the right quite a bit just to see a little bit of growth, there's still no horizontal asymptote or anything capping this thing out. So this will continue to grow higher and higher and higher as x goes towards infinity. Therefore, my range is going to be all real numbers. So I think I'll just say all real numbers. And you can say from negative infinity to positive infinity if you felt like it. This y value here is always what? I need a mathematical word that describes the y value of this function. This y value is always, and the math word I'm looking for is increasing. Okay? Alright, y prime. The derivative of this function, which talks about the slope of the tangent line to this function over and over and over again. The slope of the tangent line is always what? Slope of the tangent line is always positive, so greater than 0. That means your y prime always has to be greater than 0 because the slope of the tangent line is always greater than 0, which is also coinciding perfectly with the fact that y is always increasing. Now the second derivative, however, deals with concavity. When you just look at this graph looks like it's always concave what? This is always concave down, therefore the second derivative is always less than 0. Okay, y is concave down. And the definition of concave down tells us that the slope of the tangent lines is decreasing. And look, aren't the slope of the tangent lines going down? So we have a very steep positive slope of the tangent line, slope of the tangent line here. It's still positive, the slope of the tangent line is still positive, but not so steep. And I know you think it's probably going to flatten out to be 0, but it's never going to actually equal 0, and that's because I have no horizontal asymptote. So we have your domain, your range, y is always increasing, the first derivative is always positive, the second derivative is always negative. Now we can review a few of the rules for logarithms. I think I'll do that for a moment here. The natural log of 1 is equal to 0. Your base on your natural log is Euler's e, so e to the 0 equals 1. That should make sense to you. So natural log of 1 is 0. Natural log of a to the n. Do you remember the rule that says you can take this exponent right here and you can bring it down in front as a leading coefficient in front of your natural log? So the natural log of a to the n is n natural log of a. And then if your powers are being multiplied, you go ahead and add your exponent. So that's what this is saying. Natural log of ab is equal to the natural log of a plus the natural log of b. Natural log of a divided by b follows the same logic. Your powers are being divided here. When you divide powers, you should be subtracting exponents. We do remember, right, that a logarithm is an exponent. So the exponents are being subtracted here. Natural log of a minus natural log of b. And then the two new rules that you have deal with how to find the derivative of a natural log. The derivative with respect to x of just natural log of x is 1 over x. As long as x is greater than 0, we already know x is greater than 0 because it doesn't make any sense to talk about a negative x value if I don't have any negative x values. So this is kind of redundant, but I'm going to put it here because when we go backwards on this, when we do the antiderivative, we've always got to make sure that x is positive. And that's where those absolute value symbols are going to come into play later on. All right, and then a more generalized form of the same derivative says that the derivative with respect to x is the natural log of u, meaning u is a function of x somehow or another, is 1 over, you copy whatever the natural log is being applied to, just like you did here with the x, copy this, whatever it is, and then take the derivative of this value with respect to x. So du dx is sometimes called u prime, just like dy dx is sometimes called y prime. And instead of chasing this with a y prime, some people keep the formula as u prime over u. As long as, again, u is greater than 0, which is right here, it's just part of my domain again. Okay, the domain element that you're putting into the natural log function has to be positive in order for the natural log to be defined. So, again, it's redundant. We should know it's positive, but I'm just emphasizing that point with you. All right. Now, we're going to have to know how to break this down without using a calculator, so we're going to have to understand the rules. I'm just going to apply these rules over here. I have 4 examples set up for you. So the first 2 are simple multiplication and division of powers. If your powers are being multiplied, then you should be adding your exponent. So this should break down into the natural log of A plus the natural log of B. And you should write this out and then go back. And the given information told us that the natural log of A is equal to 0.8291. So put 0.8291 plus the natural log of B is given as 0.5403. So it's 0.5403. And you add those together, and I'm going to cheat for a second. I get 1.3694. And that would be the answer for the natural log of AB if the natural log of A and B individually were given as they are. To do a division, we'd simply do natural log of A minus natural log of B. Same numbers, you still pull those same decimal values, 8291 minus 0.5403. And that final answer is going to be 0.2888. Those are the 2 easiest examples. And then they get a little more difficult. I hope I have room here. So the third example I'm going to show you is the natural log of e cubed divided by ab. So I actually have a fraction here, and I have an exponent. So I'm going to be using this exponent rule. Where's my exponent rule? Right here. As well as this fractional rule. And I have a product with a and b, so I'm also going to be using this rule down here. Or right there. Alright, so this becomes natural log of e cubed minus natural log of ab. That's just your first step. Just take your division and split it into subtraction of logarithms. This exponent can come down, and I can have 3 natural log of e minus, big bracket now, natural log of a plus natural log of b. We need the bracket because this subtraction sign is applied to the natural log of ab, which is this whole entire sum of the natural log of a plus the natural log of b. This negative needs to be distributed. 3 natural log of b is simply 1, okay? Minus natural log of a, and then minus natural log of b. 3 times 1 is 3. Minus the natural log of a is given up there is 0.8291. Minus again the natural log of b, which is 0.5403. And we put all of that together. And if you wanted to put the 2 negatives together first, that is on my paper as 1.6306. Oh, no. Copied that wrong. That's my final answer, 1.3694. And now you know the answer is 1.6306. Okay? That's my example 3. I think I'm going to erase 1 and 2 just to put example 4 right there, if you don't mind. I don't want to go too far to the side. And I will fit example 4 right here. Example 4 is going to say the natural log of a times the square root of b. Now, can you think about what properties you're going to apply here? I definitely have multiplication between a and the root b, but then this square root symbol can be written as an exponent. And I'll be able to use my exponent rule right here. Let's just take it one step at a time so everybody's clear and everything's easy to follow. This is the natural log of a plus the natural log of the square root of b. Now I could go ahead and put my number down right now, but it's just easier for me to copy natural log of A than it is to substitute my number yet. Plus natural log, and the square root of B is known as B to the 1/2. And now this exponent can come down to the outside and become the leading coefficient on this natural log piece. So natural log of A plus 1/2 times the natural log of B. Natural log of A is 0.8291 plus 1/2 the natural log of B, which is 0.5403. We add this together. I'm just going to take half of that for a minute. Half of 0.5403 turns into 0.270 and then 15. Because 3 doesn't divide by 2, I end up with an extra place value right here. Add these together and I get 1.09925. And that would be my final answer. And those are my first 4 examples of my properties of natural log. I'm going to quit here and I'm going to come back in just a minute and we are going to go into the differentiation part. I'm going to erase the board. All right? Talent out.